Okay. Okay, hi everyone. So we're gonna continue our exploration of web, and hopefully I'm not so sick that I become unintelligible halfway through. Okay. So last time we gave you a quick whirlwind tour of web. I'm not gonna. Okay, everyone can see this. Okay, as you can tell, I'm sick. I'm forgetting things left and right. Okay. So last time we told you about different parts of the web. So we talked about the URL, how it breaks that into different paths, or like different parts, the protocol, path, location, the domain. Then we talked about how when you get served a web page, you get the way that the web page looks nice is that you're provided with HTML, which is a language that lets you do things like bold text, italic text, and so forth. And then links, forms, images. CSS makes the website look nice, so it lets you define styles, like what colors you want to use, what fonts you want to use. And then JavaScript is browser-side code, right? Key part of JavaScript is that it is not the server executing JavaScript in most cases. The server sends the JavaScript over, and then it is the browser's job to execute the JavaScript on your computer. So when you're playing that little game in your browser or something, very likely the JavaScript is executing on your computer, and it was sent to you by someone who you might not know or recognize. Okay. And finally, we talked about different threats on the internet, and the main one that we thought about was how do we protect two websites that are unrelated from accessing each other's resources? Like if I am attacker.com, how am I going to stop attacker.com from accessing resources on, say, bank.com or some legitimate website? And so the browser enforces a rule, which is that if two websites have different origins, they cannot read data from each other, send data to each other. And the way that we define origin is we just did plain old string matching on protocol, domain, and port. And that's the best we can do because same origin policy. It was not designed when the web first came about. It is something we added on at the very end. Okay. So that's all from last time. So this time we're finally going to start. Okay, fine. One more. So last time we talked about HTTP. That was the set of rules that we use to send messages back and forth. We talked about how it is one request to one response, always one-to-one, and how the request and the responses have to be formatted in a very specific way so that both sides understand the semantics of all the ones and zeros that get sent over the channel. Okay. So yeah, finally, we can talk about attacks for today. So we're going to spend the first half talking about a critical feature that keeps the web running. So the first half is not going to be necessarily attacks. We're just going to talk about what are cookies, why are they necessary to keep the web running, and then we'll talk about session authentication, which is going to look really similar to cookies, but it's really a specific application of cookies. So you can use cookies for all sorts of things. Session authentication is a very common one. And then finally, we'll talk about an attack that you can do on cookies called CSRF, and then we'll talk about defenses. So that's our plan for today. We'll talk about cookies, and then we'll talk about an attack you can do on them. Okay. So first, I'll tell you all about cookies. So one thing you might have noticed with this HTTP protocol is that it's one request for every response. So you can almost think of it as like every request and response is independent of each other. So if I send a request, I have no idea what the contents of the previous requests were, and I have no idea what the contents of the future requests are. So you can think of it as every single request to the server is processed independently of all the others. And so maybe this is okay. Maybe if you just want to fetch a PDF, it doesn't matter if you fetch it now or fetch it 10 days from now. Maybe the request and the response is independent after all. But maybe that's not what you want on your website. So here are some examples of places where if I enable some setting or I want the HTTP response to be different depending on what the past HTTP request and response said. So for example, if I go to a website, like I go to our course website, CS161.org, and I turn on dark mode, well, I would like it so that if I send any future HTTP request to the server, I want to get back websites that are nice and dark, black background, right? Or if I turn off dark mode, then I want all my future requests to have light mode enabled. So somehow I have to remember this state across different requests. So it's no longer the case that every single request and response is independent, because if I choose to enable dark mode, I want all my future requests to come back with that beautiful black background and white text. Or another example is if I type in my username and password to log into the bank website, I would like all my future HTTP requests and responses to know that I am the one, I'm the user making those requests. I don't want to have to log in again and again every single time. It's just kind of annoying. So I want my requests to remember something from the past, namely like my login information or whether I selected dark mode or light mode. Like I want some of those things to be remembered. So the way that we're going to unlock that, HTTP by itself can't do that. HTTP treats every request and response separately. So the way that we're going to unlock the ability to link together HTTP requests and responses is something called cookies. And so it's a fancy way of saying a piece of data that's going to be maintained across multiple requests. So here's how you might use it. So one way that you might get a new cookie created. So I guess the first question is, where do these cookies come from? So one way that you can create a cookie is the server can send one back to you. So when you send a request to the server has to send back exactly one response. And that response might say something like, here's the response in HTML or whatever. And by the way, here's an extra cookie that you should store and keep track of. So the server can create a brand new cookie and send it to you. And the HTTP protocol specifies where the cookie would be sent so that both sides understand, okay, this is a brand new cookie that the server has created out of nowhere and is providing to the browser. There are also other ways to do it. So if you run JavaScript, JavaScript could create a brand new cookie sometimes, depending on the settings of the cookie. You can also go into your browser settings and create your own cookies. Like that's probably pretty unusual for most people using the web. But if you really wanted to, or you wanted to execute some attack, you could certainly go into your browser and create all the cookies that you possibly want. So that's totally okay. In general, cookies are stored on the web browser. So just like how JavaScript is totally browser side, is the browser executing all the code, cookies are totally stored by the browser. So the server, the server might keep some information about the cookie, but usually we assume that this browser is the one responsible for keeping all the cookies. So if the server creates a brand new cookie, sends it in the HTTP response and says, here's a new cookie for you, the browser is responsible for keeping track of it in something called a cookie jar, which kind of makes sense. Or if some piece of JavaScript creates a brand new cookie, we would like it so that the browser keeps track of that newly created cookie also in the cookie jar. Okay. So, well, what good are these things after you create them and you store them? Well, the nice thing about them is that now, anytime you make a request, like an HTTP request from your, okay, are we back? Okay, we're all the way back? Okay, I think we're back, okay. So before I was so rudely interrupted, I was telling you about how cookies are automatically sent by the browser. So the browser digs through the cookie jar, finds all the relevant cookies, and then attaches them and sends them as part of the HTTP request. Okay, sorry, I'm sick and the Wi-Fi is broken. Okay, bad day. Okay, so now let's peek inside a cookie and see what exactly is the data and how do we store it. So just like how HTTP had all those rules about like, you got to check get or set for every single, or get or post for every single request, and your responses have to have an error code inside. The cookie also has some semantics that tell me when I build a new cookie, this is how I organize it. So I'm not just writing like an essay about the data inside the cookie. I need to format it in this very specific format. So this way, whenever cookies get sent back and forth, everyone knows exactly what I'm talking about. So these are all the fields that you have to know. There are other ones out there that you can set. Some of them are optional, some of them are mandatory, but these are the ones that you have to know for this class or for the attacks that we're going to see. So the first thing that we're going to see is that the actual data of the cookie is stored in a name value pair. So think like Python dictionary, or think a hash map, if you're more familiar with like Java or data structures. So think about mappings of names to values. So in this cookie, the actual data that is being stored, like what's the information about the website that's being stored, the name is theme and the value is dark. So maybe I wanted to keep track if someone chose dark theme or light theme, I could make a new cookie with the name theme and then map that name to the value dark. Or you can do something else. It's up to you, right? But this is what at least we've chosen on this example as the data of the cookie. And these can just be any arbitrary strings. There are some restrictions of special characters you can't use that you'll encounter on your projects, but for the most part, strings. Okay. Then we need to say something about what websites is this cookie associated with? Because if I just say theme equals dark, does that refer to like every website in the world? Does it just refer to the 161 class website? Does it refer to you on Google in dark mode too? Like, who does this cookie belong to, or who is it relevant for? So the way that we're going to do that is we're going to write a domain for the cookie and a path for the cookie. And these might look kind of familiar. They look kind of similar to the domain and the path of a URL. But ultimately, these are, or I guess they kind of do look similar, right? But they're fields of the cookie. So when you build a new cookie, you need to fill in a new domain of your own, and you need to fill in a new path of your own. And you can choose the values that you put here. And these values somehow scope the cookie and tell me about which websites is this cookie relevant to, and which websites is this cookie not relevant to. And it should remind you a little bit of URLs, although it is not an actual URL. Like when you put these together, like it's not a real URL. It is just telling me that this is relevant to this domain and this path. Okay. And we'll see later rules for how you might be able to set this, or what you might be able to set them to. Okay. Then there's two security fields that we care about. So I'll go through them one by one. So one of them is called the secure attribute. And it's kind of a, I don't know, like not the greatest name, but basically the idea is if the secure attribute is set to true, then this cookie will only be sent if the request is made over HTTPS. So do you remember how there were a lot of different protocols? The ones that we care about are HTTP and HTTPS, the secure version. So if you set the secure attribute to true, as the browser digs through and like looks for all the relevant cookies, the browser is going to say, okay, this cookie is tagged secure. So I'm only going to send it if the request in question is an HTTPS request, encrypted with cryptography over the network somehow. And if it's HTTP, I will refuse to send this cookie. And there's another attribute for security, which again, I don't really like the name. It's a little bit confusing, but it's called, I didn't invent it, so I can't name it. So it's called HTTP only. And this attribute says, if you set it equal to true, then JavaScript is not allowed to see this cookie. So we know that JavaScript runs in the browser. And since JavaScript runs in the browser, it can look through the browser for stuff like, hey, what are all the cookies being stored? Which cookies do I have? Which cookies do I not have? Can I create some new ones? But the browser will add an extra rule, which is that if the HTTP only is set to true, then we're not going to allow JavaScript to see this cookie. So JavaScript, when it asks the browser, hey, what are all the cookies in the jar? The browser will not return a cookie where HTTP only is true because we're not allowing JavaScript to read it or modify it. So yeah, I don't really like the name HTTP only, but remember, what is it actually about? It's not about like HTTP versus HTTPS. It's specifically about whether JavaScript allows you to access the cookie. Okay. So those are the fields. Again, you set them either true or false. And then there's an expiration field, which is kind of what you'd expect, which is as soon as that date arrives, this cookie is expired and you can no longer eat it or send it to the websites or whatever. So there's a timestamp that tells me when the cookie expires. And again, there's more fields, but those are the ones that you have to know for this class. Okay. Questions? I should probably blow my nose. I was doing this in 61 V lecture too, and everyone's like, I don't know. Everyone was amused by it. Okay, here we go. Okay. I hope you enjoyed. Okay. And I'm back on. Okay. So let's talk about rules for setting and sending cookies. So this is definitely going to get a little bit into the weeds of rules and like trivia, but still it's important to know as we design attacks about cookies. So first we should remember that who is allowed to create new cookies? Well, the server can create a new cookie, fill it in with, as of now, whatever they want, and then send it to you. And then the browser is going to automatically attach any relevant cookies. And we haven't formally defined what it means for a cookie to be relevant. And we also haven't formally defined rules for what kind of cookies you can set. And we're going to see now why we would need those rules in the first place. So for example, it would be kind of annoying if, say, like I made a request to evil.com and then evil.com sent me back like, hey, here's a brand new cookie for you. Please store it. And that cookie is marked as relevant for like CS161.org dark mode. So somehow I've talked to evil.com and they've sent me a cookie that forces my CS161 website to be dark mode. Like that's kind of weird, right? I don't want websites to send me cookies that get used on unrelated websites. So somehow that feels like a risk. It feels like somehow I'm subverting the same origin policy and allowing two websites to communicate when they shouldn't be able to. So we're going to have to add rules to prevent this case. Because anybody can set a cookie, but I don't want the evil.com website to send me back a cookie that ends up affecting future requests to CS161.org. Because if they send me a cookie and it says like theme equals dark CS161.org, in the future, anytime I make a request to CS161.org, I might end up sending this evil cookie and suddenly my website's in dark mode and I'm like, what the heck is going on? So I don't like this. It's a security risk. We have to take care of it. And a second problem is that cookies can often contain sensitive information, as we're about to see. So suppose a cookie contains some like top secret information. Well, it would be really bad if I had a cookie with top secret information about my bank account login or something really sensitive, like, I don't know, password to like the exam solutions. And when I made a request to evil.com, it would be pretty bad if my browser decided to take that cookie, attach it, and send it to evil.com. Again, it feels like somehow I'm breaking the same origin policy and allowing two websites to communicate when they shouldn't. So somehow I need to prevent cookies being sent to the wrong places because the browser is automatically attaching relevant cookies. I need to define this word relevant in a way that cookies don't get sent to the wrong place. If I have a cookie that has a secret from my bank account, it should really only be sent and attached to my bank account requests, not to any other requests. And also, if evil.com sends me a cookie, they should not be able to send me a cookie that affects other websites. They should only be able to send me cookies that affect their own website, evil.com, the website setting the cookie. Okay. So now we have to come up with rules to do all this, and it's called cookie policy. And just like the same origin policy, these are enforced by the browser. And why does it make sense for the browser to enforce these? Because where are the cookies stored? They're stored in the browser. So when the browser gets a new cookie and someone says, hey, here's a new cookie for you, please throw it in the jar, the browser is going to check, is this cookie okay, or is it disallowed and I shouldn't accept it? And likewise, when the browser is automatically attaching cookies in every single request, it's the browser's job to check, is this cookie relevant to the request being made, or is this cookie totally unrelated and I probably shouldn't send it? So the browser is the one who has to decide all of this stuff. And one thing I'll note is that the rules that you're about to see, these are specific to cookies and how they get sent. They are not the same thing as the same origin policy, even though both of them serve kind of the same purpose, which is to stop websites that are unrelated from interacting or affecting each other. But this one is specifically a set of rules on cookies, and same origin policy is specifically a set of rules on like HTML. Okay. So before I can tell you about all the cookie rules, we need to take all these domains and somehow organize them, because if I have a bunch of domains, like, I don't know, I have berkeley.edu, CS161.org, google.com, I would like to be able to organize them in some sort of way so that I can define very specifically, what does it mean for domains to be related? What does it mean for a domain to be more specific, less specific? So the way that I'm going to do it is kind of what you'd expect, which is you look for all the dots in the domain and you split the domain on all the dots and you create a kind of natural looking tree like this. Like, honestly, I don't know how to explain this without just showing it to you. So it seems pretty natural to say berkeley.edu and mit.edu, they both belong to the family of .edu domains. It seems pretty natural. And, piazza.com, not that we use Piazza anymore, but, remember when we did, and google.com, those seem to belong to the family of .com. And every single domain belongs to the family root. So that's the set of all possible domains. So we'll see this again also in a lot more detail when we talk about DNS. But for now, you can think of the domains as somehow forming a tree. And this tree can allow me to specify things like which domains are more specific, which domains are less specific, which domains belong to a family, which domains don't. So that's why the hierarchy exists. And so we can use this to start building up all of our cookie rules. Okay. A couple more just like vocabulary terms that you'll see now and then. Sometimes when the domain is directly below root, so it's got a single dot followed by something at the very end, sometimes people call that a top level domain. So anything, the whole family of .edu, that's the .edu top level domain, or the family of all domains ending in .com, all the servers whose names end in .com, that's the .com TLD. There's one for, I don't know, .co.uk for all the British ones, I don't know, lots of different ones. And sometimes we use the word subdomain to say when something is more specific. So eeks.berkeley.edu, it seems pretty natural to hang it underneath berkeley.edu in this tree. So we can say something like eeks.berkeley.edu is a subdomain. So just vocabulary on this slide, nothing like super fancy. Okay. So finally, we can get to the rules. So first thing to remember when you see these rules is like, what are they even good for? Like the browser is the one checking them. We should remember that. And we should also remember the reason why these rules exist is to stop those attacks from earlier. So if the evil.com website sends me a cookie, I need to decide, do I accept this cookie and add it to my cookie jar? Or do I deny this cookie and throw it in the trash? And the reason why this matters is because I don't want evil.com to send me a cookie that can affect other websites. I don't want evil.com to send me a cookie that like changes my bank login or I don't know, changes my 161 to dark mode. So somehow I have to come up with some rules. And so this is kind of an annoying way of writing it, but all of these mean the same thing. So I'll first say it in like words, I guess, and then I'll show some examples, which might be more helpful. So one way of saying it is that there are two domains that need to be compared here. So remember, when you get a brand new cookie, it's got a domain inside. Like, do you remember when we showed, what was this? The parts of a cookie, domain right there, right? So there's a domain inside the cookie. That's one of the values that we have to compare. And the second value that we have to compare, and that was the value in red, that's the domain inside the cookie. But there's actually a second domain that we care about, which is the domain of the website sending me the response. So if I send an HTTP request to say like www.google.com, when I receive a response, who is the response coming from? It's coming from www.google.com. So these two values, even though they are both called domains, the one in blue, that refers to who is sending me the response in the first place. And domain attribute Y refers to what did that person fill in when they created a brand new cookie with a domain. So what I have to do to determine whether I accept this cookie or not is I have to check these two values, and I accept the cookie if, and again, the wording is kind of funky, but one way of saying it formally is that the domain attribute, this is the thing inside the cookie that the server wrote down, is a domain suffix of the server's domain, which is the website sending the cookie back to me. So a couple ways of saying this in maybe more palatable terms are, you could say that value in blue, which is the server sending, like the identity of the server sending me the response, that string has to end in Y, the domain attribute. Another way of saying it is that the domain has to be below or equal to, has to be more specific than Y, or you could say X is more specific or equal to Y. All of those actually are exactly the same. And if those still sound confusing, honestly, you're not alone. I think examples make this a lot clearer. So here's an example. I sent an HTTP request to mail.google.com. This is the value in blue. Why is it in blue? Because this is the person I'm talking to. I made an HTTP request to mail.google.com, and they're sending a response back to me. So this is the domain of the website sending the response back to me. And when they send a response back to me, they could invent a brand new cookie. You know, like they baked a brand new cookie and it's got a domain value and a path value. And the server, mail.google.com, decided to write in google.com for the domain field. They chose this value. It's baked inside the cookie. And so I'm going to label that red. This is not who I'm talking to. I'm talking to mail.google.com. But when they cooked up that brand new cookie, they decided to write google.com as the domain field. So I check, and I can check this all sorts of different ways. I could check, does mail.google.com end in google.com? Well, it sure does. Mail.google.com ends in google.com. So that's okay. We accept this cookie. We could also say, is mail.google.com going to be below google.com if I drew the hierarchy tree? It would, in the same way that eeks.berkeley.edu was underneath berkeley.edu. Mail.google.com will also be below google.com. So I accept this cookie. We could also say mail.google.com is more specific than google.com, also a way to accept this cookie. So in other words, if I receive a cookie and the value has domain google.com, I will only accept if the person setting the cookie is google.com or someone below or more specific than google.com. Okay. And as another example, if mail.google.com, or if I made a request to say like evil.com, so now the blue value is evil.com, and they sent me back something with domain google.com, now evil.com is not more specific than google.com. They're not below each other on the hierarchy, or one's not below the other on the hierarchy, so I don't accept. If evil.com tries to set a cookie that's scoped to google.com, I don't accept, right? This stops unrelated cookies from being accepted if they come from someone unrelated. Okay. And just like we said from before, if you make a request to google.com and you get an answer from, or you get a cookie with domain google.com, also accepted because google.com, it ends in google.com. Yes. Is google.com below or equal to google.com on the hierarchy? Well, yeah, they're the same thing on the hierarchy. Is it more specific or equal to google.com? Yes. So ultimately, once you get the hang of it, it is a little bit mechanical. But the important thing of why it's set up the way that it is because I don't want evil.com to be able to set a cookie that messes with bank.com or messes with CS161.org. That's the reason why this whole policy exists. But ultimately, the policy is a little bit like trivia. You just kind of write it down somewhere and keep track of it. Okay. A couple more just side notes, and I know we're getting into the weeds of these policies a little bit. So one thing you cannot do is you cannot have the domain attribute be a top-level domain. So for example, you would not be allowed to set domain equals .com. And if you think about, again, the reason for doing all this, it feels pretty reasonable that I don't want to set a cookie for domain.com. Because if I set a cookie for domain.com, I'm saying like, this cookie is relevant to every single .com in the world. And it's like, well, that seems kind of weird. How is evil.com able to set a cookie that's relevant for all the .coms in the world? Like evil.com should not be able to speak for all the .coms in the world. And google.com should not be able to speak for all the .coms in the world. So somehow this .com domain, if I fill in my cookie fields and I write .com as the domain, then I'm somehow claiming to speak for all the .coms, and that's just too general. So we added another extra little side rule that says if the domain attribute is a .com, you can just stop right there and say, no, I don't accept. Because .com is too general. I don't want to set cookies that affect everybody in the .com subtree, or I don't want to set a cookie that affects everyone in the .org subtree. It's way too general and opens up too many attacks. So we add this extra rule, which is that the domain attribute, the thing you fill in the cookie, it better not be a .com or a .org or one of these top level domains. Okay. Final little nit that I have to mention is that we actually don't check the path for setting cookies. So you can set any path you like. That's just the rule. Okay. So maybe it'll make more sense once we see the policy for sending cookies. But it turns out when you're setting cookies, you just check the domains against each other. And the server sending you the cookie, they have to fill in a value for the path. And when the cookie had all those fields, the server had to fill in something for the path. Turns out they can put whatever the heck they want. Any string goes, the browser's not going to check that and reject. Okay. Yes, I know it's a little bit tedious, but that's the policy. And the important thing to remember is like why the policy is the way that it is, right? The goal is to prevent someone like evil.com from setting a cookie that would affect other websites as well. There's a question of where are the cookies stored? They're stored in the browser, right? So the browser is the one responsible for keeping track of all the cookies because it's the one collecting all the cookies from websites and then attaching all the relevant ones as they get sent out. Yeah, great question. Anything else? Yeah. Do we have to satisfy the three conditions? Yeah. So, okay. So the question was, these three conditions, do I have to satisfy all of them? They're all equivalent. So these are just three different ways of writing the exact same condition. So if you satisfy one, you satisfy all. Yeah, great question. Okay. So that's setting cookies. So I have to go through the other half of cookie policy. And again, I know it can be a little bit boring at this point, and we're really getting into the weeds of this stuff. But remember, like the big picture is that I want to be able to attach cookies that are relevant. So when I make a request to google.com, I'm going to dig through all my cookies. I might have a cookie saying like CS161.org dark mode. I might have a cookie saying, here's your bank.com login. And I might have a cookie saying evil.com something. So somehow the browser needs to be able to dig through the entire cookie jar and extract all the cookies that are relevant to the google.com request that I am about to make, and then automatically attach those in the HTTP request that I fire off to www.google.com. So how do I determine whether a cookie is relevant or not? That word relevant was just too vague. Like, what does it actually mean? So here's where we're finally going to define what it means for a cookie to be relevant. So again, there's two domains and there's two paths. And I feel like it's kind of confusing at first. Well, how are there two domains? So remember, the thing in red, these are the values inside the cookie. When I create a brand new cookie, I have to fill in all those fields. I got to fill out the whole form. And two of the fields that I have to fill out are the domain and the path. So that thing in red, that's the thing I fill inside the cookie. And then this stuff in blue, these are the domain and the path of the person I'm talking to, just like before. So when I make a brand new request in HTTP to www.google.com, then the domain and the path are www.google.com. Okay. And the domain and the path attribute, those are buried inside whatever cookies I'm taking through. So this is what it looks like in words. And again, you can think of it as the domain attribute has to be a suffix, has to be more specific than the server's domain. The path attribute has to be a prefix, has to be less specific than the server's path. But like, I look at these and honestly, I'm not a huge fan of this. So here's my little trick for doing sending cookie comparisons. It does not have to be your trick. If you really like thinking about suffixes and prefixes, you totally can. But here's what I do. So I write the two values side by side. And I guess the colors are a little bit funky, but this thing on the top, this is the person I'm talking to. I made a brand new HTTP request to this thing up top. So that corresponds to these values, the ones in blue. So that's the person I'm talking to. I make a brand new HTTP request to this URL. And now this browser needs to go through every cookie one by one and decide, are you relevant? Should I send you or should I not send you? So consider a cookie whose domain is this and whose value is this, or path is this. Like, where do these values come from? They're inside the cookie. They're baked inside the cookie. When I make a brand new cookie, these two values are baked inside. So what I can do is I can just line them up really carefully like this. So I can take my cookie domain, my cookie path, and then put them together. and line them up at the right place. So like wherever that single slash is after the first domain, I line them right up. And then all I have to do to check is I check the domain starting at the slash and going backwards. And it seems like I have found a total match. The 161.org matches the tune.161.org. And I go to the right and I check. Does that match that? Yes, the paths match all the way to the end of the cookie, right? And so if I start at the slash and I move to the left and I move to the right and everything matches with the cookie domain and the cookie path against the URL that I'm sending to, then I consider this cookie relevant. Whatever name and value pair is associated with this particular cookie, I will attach this cookie and send it to this URL. However, if I get something like this where the path just doesn't match, then I check to the left, it's okay, but I check to the right and I see a mismatch and I don't send this cookie. So this is just exactly the same as the definitions from before, where like this word is simply not a prefix of this word, that's okay. Or you can just put them side by side and do a comparison. Again, it's kind of mechanical, but the important thing is I care about cookies that are relevant, and this is how we're defining a cookie that's relevant. Okay. So those are the policies. We talked about setting cookie policies. Those tell me when I get a brand new cookie, do I accept or do I reject? And I need to make sure I only accept cookies that are relevant. So I avoid the attacks like evil.com sends me a cookie that's relevant for like bank.com, that would be bad. And when I send cookies, I use this rule to check whether or not the cookie is relevant. If it's relevant, I send. If it's not relevant, I don't send. And again, I know it's not the most interesting thing in the world, but it's important to remember what these policies are and be able to like check, because when we start doing attacks, it's important to know which cookies are relevant and which ones aren't. Okay. Okay, great. So hopefully some more interesting stuff coming up. This one is kind of interesting. Unfortunately, it's just a lot of slides and a lot of words. But if you're interested, it's here. I think we also have a video from the past semester talking about it. It's called the Spectre attack. And this is one of those attacks where the people writing the operating system messed up. So when the people writing the operating system messed up, a lot of bad things happen. And we actually walk you through the details. It's actually something you know how to do, given your knowledge of memory safety and how the browser was memory unsafe. And also now given your knowledge of cookies, but I'm not going to say it all right now. But it is pretty cool. So it's there if you want it. It is very long and complicated, but if you're interested, check out the video on it from the past semester. Up to you. Okay. But I guess one thing I'll note about the legacy of this attack is like, if you ever wonder why your browser eats up so much memory, it's because of this attack. We had to somehow keep all the tabs separate. And to do that, we have to run different processes for every tab. And that's what makes web browsers so like memory consuming or intensive. Okay, so now you know there's this vector attack. It's not something we would test you on, but turns out, just given all the first principles you know now about cookie policy and about memory safety vulnerabilities, you can reconstruct this, which I think is really cool. Okay, unfortunately, we won't because I don't have time, but pretty cool. Okay. Anything else you want to know about cookies before I tell you about an application of them? We talked about what they are, the policies of when you set them, the policies of when you send them. Now we can finally talk about the rules, or not the rules, but like the applications of what cookies are good for. Okay. So we already saw a couple of uses. Like one of them was the dark mode thing. So somehow when I send a request to the server and I say, I would like dark mode from now on, the server can reply to me with a cookie and saying, sure, you want dark mode from now on? Keep this cookie in your pocket. And every single time you make a request, please attach that cookie and I will remember to send you the dark mode website every single time you ask. So that way I've made my HTTP requests and responses not independent. They can now rely on each other, which is pretty cool. So that's one possible use of cookies. But another one that's really common and security sensitive is staying logged in. So for example, if I walk up to Gmail and I log in a single time, well, that login is a single HTTP request, and my response might be like the list of all my unread emails. Well, that's great. But later, if I make another request, how does Google still know that I'm logged in? Like it doesn't know, right? And so without the power of cookies, every single one of these requests would be independent. And I would not be able to stay logged in as a user if I wanted to say like check my email all day long. So that's why we need the power of cookies to help us unlock something called the session. And what's the session? It's a fancy way of saying when I log in, I usually stay logged in for a certain amount of time. And how is it even possible to stay logged in? Like how does the server know all those future requests are coming from you? That's because there's some cookie being set that reminds the server, oh, hey, here's the person who's currently logged in, making all the requests. Okay. So if it were not for cookies and session authentication, how would you deal with the internet? You would have to type in your username and password literally every time you open your email client. Every single HTTP request would have to have the username and the password attached because they're all independent. They cannot rely on each other. And then every response would be separate. So kind of annoying. Like I don't want to have to type in my username and password every single time I want to check my email. So instead, I want to be able to associate a bunch of requests and responses with the same logged in user. So I log in a single time, provide my username and password, and then for like the next 15 minutes or 1 hour or 1 day, all the requests with the same somehow like cookie attached or somehow the same something, and we'll have to figure out what that something is, are associated with the same logged in user. So how do we unlock this? We unlock this using cookies. So this is an application of cookies. It's not the only thing, it's not the only thing you can use cookies for. You can also use cookies for, dark mode or something else. But this is a very common security sensitive application of cookies. Okay. So anything else you want to know about this stuff while I try to like stay alive up here? Okay. Okay. Okay, don't come up here later or else you're gonna like get germs all over yourself. Okay, so here's the intuition for maybe what session authentication is going to look like. And so maybe it helps, maybe it doesn't, but it's something we thought of. So I don't know if anyone's ever been to like concerts before or still goes, but if you ever go to a concert, maybe what's happened is like the first time you walk in, like you're waiting in line and you go in and the security guard asks for your ticket and asks for your ID. So you present, here's my ID, here's my ticket. They scan the ticket, scan the ID, check that you are who you say you are. And then has anyone ever gotten like a wristband? They give you a wristband on your way in, right? And so what is the point of the wristband? Well, the point of the wristband is say you forgot something. You're like, shoot, I left something in the car. So what would you do? You would leave the venue or wherever the concert is taking place. And if you want to come back in later, do you have to wait in line and show your ID all over again? Well, no, you just show the wristband and tell them, you've already checked me. Here's the wristband. And then they let you back in. So somehow this is what we want. Because if all of the incoming people into the concert were like treated independently, when I leave and re-enter, I would have to present my ticket over and over and over and over again. And the security guard would have to check my identity over and over and over again. But instead, if I walk in a single time, I get a wristband. The wristband basically says, yes, this person is already authenticated. So the next time they walk in, you don't have to go through that costly check of like, here's my ticket, here's my ID again. You just show them the wristband that's automatically attached, and then they let you right in. So this analogy, like it works for the most part. I guess the one place where it breaks is that the wristbands would have to be unique for every single person when we talk about session authentication because everyone's logged in separately. But like modulo that one little nitpick, this I think is a pretty natural analogy for session authentication. Okay. So what does this thing look like in actual cookies? So the thing that I want is I want that wristband, but I want it in cookie terms, or I want it in session terms. I don't want like, physical wristband. So how do I take this idea of a wristband and turn it into something that I can actually implement? So I'm going to implement it using a value called the session token. And this is a very fancy way of saying this is a random long secret value that is associated with a currently logged in user. So if I am logged in right now, I have a session token. It's a long random string that identifies who I am and the fact that I'm currently logged in. This is the wristband sitting in your browser. So how do you get one of these wristbands? Well, I have to wait in line, show my ticket and ID, and get a brand new wristband. So in that same vein, the first time I log into the website, I present my ticket, my username, my ID, my password. They check if I am who I say I am. And if they're satisfied, then they provide me with a wristband. So how does the server provide me with a wristband? They send me the brand new session token that I've just created. Now I have a wristband on me. So in the future, if I ever want to make another request, like I want to check my email again, or I want to go back into the concert, I don't have to wait in line and show my username and password all over again. I don't have to type my username and password again and again and again. Instead, I can just take that wristband, the session token that I've already received, attach it in my request and say, hey, remember this value that you gave to me earlier? Remember this wristband? I still have it, so you know who I am. It's me. And so the server looks at that value and says, oh yeah, that's you. And so they accept that response as being from you. and you no longer have to enter your username or password, which is really nice. So that's the wristband as it would be implemented in code. It's this random value. You receive it the first time you log in, and in the future, you send it to the server every single time. So who has to remember the session token? Well, we have to remember it, the person using the website. We have to keep it in our browsers, because in the future, if I ever want to check my email, I need to resend that session token over and over and over again. And also, this time, the server also has to remember that session token. So it might have some sort of database that says, like, this user is currently being issued this token. This user is being issued this token. So that way, when I send that token over and say, hey, it's me, remember me, the server can look in their database and say, oh yeah, I remember you. I gave you this token, 10 minutes ago. That's who you are. So I'm going to associate this request as being from you. Okay. So this idea of session tokens is really great, but at this point, it's really tempting to think session tokens or cookies. Are they the same thing? Are they related somehow? They are, and the way that they're related is that the session token is just some high-level idea. It's like this wristband idea. I didn't say anything about cookies on this slide. It's just some arbitrary idea. You can implement it however you want. But it turns out the most natural way to implement it is to use cookies. So session tokens are the idea. Cookies are how I implement them. And as we said from before, this is not the only use of cookies. You want to go use dark mode, go use cookies. You want to go, I don't know, whatever you want, right? I can't think of any right now. But there are all sorts of different ways to use cookies that do not involve session tokens. But session tokens are one common application of cookies. They're a high-level idea that I'm going to implement using cookies. So I'm going to rewrite the same steps from before, but this time I'm going to use cookies to actually store that value. And we'll see it's actually pretty natural. So first time I log in, I send my username and my password like I always do. The security guard checks my ID. Yes, you are who you say you are. And this time, instead of just sending you the session token, they're going to send you a new cookie. And the cookie is going to have the session token inside. And just like before, the server is going to keep a map saying this new value that I generated is associated with this current person logged in right now. And in the future, if I ever make a request, well, the nice thing about cookies is they're automatically attached. I don't have to manually dig through and find the right session token. If I set the session token up correctly, the browser will just automatically attach the session token every single time I make a request to the same website. And then the server can check the token and say, oh yeah, I remember this token. I know who you are. And so they can send you data that's customized to your logged in session. So if I send a token or I send a request and the cookie has my token attached automatically, the server knows it's from me. They will serve me my unread email. But you might have a different session token. And if you ask for your unread email, you'll send your session token. The server will check that and say, oh, I know who this is. And they'll give you your unread email. So we can make the same requests with different cookies and different session tokens. And the server can customize our responses, which is great. Okay. Session tokens and cookies, very, very similar things. But the important thing is that session tokens are implemented with cookies. Okay. And finally, how do you log out? So there's a couple ways to do it. So one way is if you explicitly click log out, then both sites destroy the token. So when you click log out, maybe like a little piece of JavaScript runs or something, deletes your token, and then the server will also delete it from their database and say, nope, this person is no longer logged in. Another way to log out is if the session times out. So maybe the session was only valid for 15 minutes or something, and after 15 minutes expire, the session token cookie might just expire. So the server might delete it, say they're no longer active, it's been too long, and maybe the cookie itself expires. So lots of different ways to destroy a session token once you're done with it. Okay. Questions? Okay. So session tokens, they are very secret values. And if you think about it, imagine if someone comes along and steals your session token. What happens if they steal your session token? Well, now they can take that same secret value, attach it to their own requests. And when the server sees those requests, what will the server think? They're like, oh, I know this value. I know who this is. But it's not actually you. It's someone else who stole the value and is pretending to be you. So session tokens are really sensitive because they are how the server knows who you are. So if someone else steals that value, they can present the same value to the server, and the server will see that value and be like, it's you, I remember you, but it's not actually you. It's someone else who stole your session token. They're stealing your identity, and now they can do anything they want inside your email account or your bank account or whatever it is you're logged into. So you have to be really careful about session tokens. they are like as good as your password. If someone steals your session token, it's like they stole your password. They can now log in as you, which is bad. Okay. So how do we stop this? The server has to be careful here because the server needs to generate these tokens very securely and very randomly. Because if the server generates the tokens like 0, 1, 2, 3, 4, well, now the attacker has a very easy time guessing what the token is. And if they guess the token right, they can pretend to be you. So the server has to be really careful. It has to generate the session tokens randomly. So one way to do this is maybe pick a really long value, like 256 bits, and make them all random bits, and use a secure random number generator. And now, if an attacker wants to guess the session token, what are their odds of succeeding? Like 1 in 2 to the 256, right? Like size of the universe, unlikely. So we have to be careful, make sure the session tokens are not guessable and not compromising them. Okay. That's the server making sure that the session tokens they create are not guessable. The browser itself also has to make sure that other people can't steal the session token. For example, if I log on to evil.com, it would be really bad if evil.com could just go into the cookie jar using some JavaScript and pull out all the cookies, including session token values, and just read them. That would be really bad because now the attacker's JavaScript can like maybe take those values, send them back to the attacker or something. Now the attacker knows all your session tokens. So the browser itself has to make sure that if you go to evil.com for who knows why, the JavaScript or any code on evil.com executing in your browser is not able to see these session tokens and steal them. And how do we enforce stuff like this? We need to make sure that unrelated websites don't interact with each other. So we saw how cookie policy would stop, maybe evil.com from receiving the cookie. We don't want to send this sensitive session token to evil.com because that would be bad. And also say same origin policy where I'm not able to access the data in some other website. So this is where we need to enforce that like separation of different websites. Okay. And finally, like we said, it'd be really bad if you had a cookie that logged you into google.com. And when you made a request to evil.com, your browser was like, oops, I automatically attached the google.com cookie into my request to the attacker. Now the attacker receives the request, knows your session token value, can log in as you. So that's where the cookie policy comes in. We only attach relevant cookies, and we need to carefully set these cookies such that the google.com session token is not sent to an irrelevant website like the attacker's website or anyone else's website for that matter. Okay, so how do we build one of these session token cookies? We know these are the fields of the cookie value. They can be filled in with basically anything you want subject to the cookie rules. So here's an example of what you might want to set. So name and value seems reasonable. Maybe call it token. You can call it session token. We call it whatever you want. The value, it's got to be long and random. We talked about this. The value cannot be something predictable. It can't be like a counter or the current date. Then an attacker could guess it, and that would be bad. So this needs to be long, random value, 256 bits, size of the universe, unlikely to guess. What about domain and path? These I need to be really careful when I set them because I need to set them so that the browser only attaches these cookies to the relevant requests. So if I mess up and I set these domains and paths to be too general or too specific, I could mess up and cause this cookie to be sent to the wrong place. So maybe if this is a cookie for my email, I'm going to specifically say the domain is mail.google.com so that this cookie is only sent to requests that end in mail.google.com. So mail.google.com will receive this, but maps.google.com would not, or evil.com would not receive this cookie because it's not relevant to those domains. So I need to set these specifically, and that depends on like how your website is organized. You need to carefully set these so that this cookie is only sent when it's needed. You should never be sending this cookie unnecessarily because it's got top secret login data. And the way that you control that is you set the domain and the path to limit this cookie. So it's only sent in the relevant cases. Okay. Should I set the secure flag to true? Probably, right? Seems like a nice idea if this is a secret value to take that secure flag, flip it on, even if I didn't know anything about what that was. But what it actually does is it would say that this cookie is only sent over HTTPS connection. So if you make an insecure connection where an attacker can eavesdrop on a channel, then this cookie would not be sent. It's only sent if the channel over the network that you're using is encrypted, which is a nice property. HTTP only, again, it's kind of on you and what settings you're using, but one possibility or one argument for setting it equal to true is because you don't want JavaScript to be able to dig and access those tokens. Like I would not want the JavaScript on some other website to be able to dig through all my cookies and find the session token, and now they know my random value. So one way to stop that is to just say, nope, no JavaScript can ever touch this cookie. If JavaScript asks for a list of all cookies, we're just going to pretend this doesn't exist and not give it back to the JavaScript. So you can do something like that. And then finally, expiration date. Again, it's up to you. But if you think that a user can only be logged in for 15 minutes at a time, and after that, they should log in again, then you might set the expiry date to something like that. If you feel differently, you're like, user can log in, stay logged in for like a day, a year, then you could change this expiry date as you feel appropriate. Okay. But the downside is, if someone sets an expiry date of like a year in the future, now this cookie is good for a year. So now that user is going to stay logged in for a year, even if, say, someone else steals the computer or something. So it's up to you, right? There's a trade-off between usability and security that we see over and over again. Okay, questions. When you log in again, is the session token different? If you're asking about two separate logins, I think it's generally true that the session token is different. So once I log out, the session token is destroyed. If I make another login request with my username and password all over again, I should get a different token. Yeah, great question. Others? Yeah.
If we set the HTTP only to choose, then how the server verify this is correct?
Question was, if HTTP only is true, how does the server know whether or not the JavaScript is correct? Well, when I send the cookie over, the server receives the cookie as part of the HTTP request, right? They don't need JavaScript to be able to access this cookie. It's sent as part of the HTTP request data. Yeah, great question. Oh, okay. I'm not getting through like the rest of the week, am I? Okay. So that's it for cookies. That's it for session authentication, which is a particular application of cookies. So the final thing we have to talk to you about is the attack on cookies. And then after that, we can go home and I can get a good night's rest, hopefully. Okay. So we've already talked about cookies and session tokens. We know how the session token is implemented using cookies, and it's a value that associates a request with the current person who's logged in, and the browser automatically attaches this stuff. So the attack here is called cross-site request forgery. It's kind of a fancy name, but basically the idea is that, well, what if the attacker tricks you into clicking something you were not intending to click? So for example, I guess we'll have examples later, but basically the idea is if an attacker tricks you into clicking something you did not mean to click, and we'll see lots of different ways to do this, when I click on something, what's going to happen? The server, or not the server, the browser is going to automatically attach all the relevant cookies, and then the request is going to be made. So if the attacker tricks me into making a request that I did not intend to make, like I was not actually trying to do it, but the attacker tricked me into doing it, the cookies will be attached because that's what the browser does. It automatically attaches cookies. And then the server will have no idea that I got tricked. The server will think, yeah, this person probably really wants to send $1,000 to Mallory, and this bank's going to make that happen. Because they have no idea that I've been tricked. They see the request, they see the cookies are valid, they see the session token matches my previous logged in token, and they give me the request, or they execute my request. So CSRF is an exploit on the fact that the browser attaches cookies automatically to allow an attacker to perform an action as me. They're going to trick me into doing something. I'm going to potentially believe the attacker and make that request. And because when I make the request, I automatically attach the cookies, the server will think that I actually meant to do that, even though the attacker tricked me. Okay, here's what it looks like in a diagram. So the first thing that happens is we actually log in. So we send the username and password, and then we receive a valid session token. So now in our browser, we've got the valid session token. The server's database also says that token refers to this person who's currently logged in. So the server knows who I am, and I have the session token that I can present so that the server knows who I am. And now somehow the attacker might trick me and say, click this link or make this post request. And if I accidentally make that request and I listen to the attacker, then I'm going to send a request to the server. And what will the browser do? The browser will automatically attach that cookie, and the server will have no idea whether or not I actually meant to do that or whether or not I was tricked by the attacker. So the server is going to see the request. It's going to have my name on it, my cookie on it, my session token, and the server is going to think it came from me. So that's basically it. It's got a fancy name. It's got all these different steps. But ultimately, all you're doing is you're abusing this fact that because of the cookies being automatically attached, any request from the user will look like it's coming from them because of those cookies. So if you can trick the user into making a request, then the server will have no idea that the user was tricked. The server will think the user actually meant to do it. So all of it kind of boils down to making the user make that request while they're logged in and automatically sending cookies. Okay. So feels like, well, easier said than done, right? Like, how am I going to get the victim into making a malicious request? Like, is everyone, that gullible that they'll just click on whatever link? So here are lots of different ways to do it. So I'm going to split into two different categories. Suppose I want the victim to make a GET request that they did not mean to make. How would I do that? There's actually lots of different ways. So one way is maybe I'll trick the victim into clicking a link. I'll send the victim an email being like, you've just won $1,000 in a new iPhone. Click on this link to claim. And if the user clicks on it, now their browser is going to open that link. And what does the browser do when it opens the link? It makes a GET request to that link to see what that link contains and fetch the information from there. So if you can somehow trick the victim into clicking a link that they were not intending to click, then that's one way to trick them into making a request. And if that request is to some authenticated server like the bank, then the cookies will be automatically attached, right? And how much you do this? Yes, you can send an email that's like, you've won, a new iPhone. You can also do other things, and we'll see those when we talk about like clickjacking and phishing. Okay. So example, maybe that link that I send in the email goes to something like this, and maybe the bank has this transfer function that is opening up to everyone. And if you send a GET request to the transfer endpoint with these arguments, maybe the bank will process your transfer. And when the user clicks on this, the user is going to send the request with these arguments, and the bank's going to process it. Why is the bank going to accept this request? Because the user automatically attaches cookies. So the bank will say, I remember you. You're the person that just logged in. And you want to transfer $100 to Mallory? Like, okay, I'll do it. And so now, all your money's gone. Okay. Other ways to do it. Maybe you just accidentally go on evil.com for some reason. And if you go to evil.com, maybe their website has some JavaScript, and we know JavaScript can also make requests. That's an option. Here's a pretty cool option, which is, do you remember that image source thing from last time where we said, if I embed this HTML on a website that someone loads and the website or the browser is trying its best to make the website look nice, how is the browser going to make the image appear? The browser is going to go to that link, get the image, and display it for me. That's what the image source tag does. I go to this link, make a GET request to fetch the image and display it to the user. So whatever link I put here, the only way for the browser to make this image appear nicely is to make a GET request and fetch the image. Except that's not actually an image link, right? Like there's probably not an image sitting over there. So even though this doesn't have an image, what's the browser going to do? It's going to say, I see an image tag. I think I need to make the image appear for the user. So I'm going to make a GET request, receive an image, and show it to the user. So I make the GET request. I receive back not an image, and I display an error. I'm like, that wasn't an image. But it's way too late, because by the time I've made that GET request and received back an error, not an image, I've already sent this GET request over, and the money is already gone. So the image source tag is one way to trick people into making a GET request. Because the only way to render this image tag correctly is to make a GET request to whatever the source attribute is and try to get the image back. And maybe you don't get an image. Maybe you just went to some endpoint that like causes some transfer to happen. Okay. So yeah, HTML will probably return an error, but by that time it's too late. The GET request was already sent. And as we know, cookies are automatically attached. No one asks you if you want to send the cookie. They're automatically attached. So by the time this request gets sent, it's too late. Mallory's got the money, and you get an error on your webpage. Okay. Great. So those are ways to trick the user into making a GET request. Those were simpler because all I have to do is get the user to click on a link or make a GET request. What about post? Post is a little bit trickier because if I just go into my browser and type a link, that's not a post request. That's a GET request. And we talked about that last time. So how am I going to make a post request happen? Well, as we said, if you just click on a link, that triggers a GET request. It doesn't trigger a post. However, maybe when you send the user an email like, you just won the lottery, click to claim your prize, maybe you make the user open the attacker's website, and maybe the attacker's website has JavaScript that makes a post request. JavaScript is able to make a post request, so that might be an option. Other options are, if you know the victim is going to visit some website, I could put JavaScript on that website. I'm like, I know the user logs on Facebook a lot. And so I'm just going to go on Facebook, write some JavaScript, and then maybe the user will run that. And that's an attack that we'll see a couple lectures from now. Other ways to do it are you could just pay for an advertisement, and the advertisement has the JavaScript. So if you ever open a page and the advertisement loads, well, now the JavaScript is going to run and it's going to cause you to make a post request. So ultimately, if you want a post request, usually involves some level of executing JavaScript on the victim's side, but still possible, right? So just because I want to make a post request instead of a get request, that doesn't mean CSRF is completely defeated. It is still possible, just a little bit harder. Okay. Well, okay. Any other questions? Okay, we're almost done. Okay, great. So this is, you've seen this over and over again. Once we talk about web attacks, we're going to check off a bunch more of these. But here's CSRF sitting in the top 10. And all you had to know was, web 1.0 basics and how cookies work. And yet, like, there it is, it's top 10. So still really common these days, even if it's been around forever. Okay. And as we go through web, we'll check off even more of these. So come back next time, we'll check off another one. Okay. Here are a bunch of examples. I'm not going to go through all of them. Turns out the Internet of Things, like the smart toasters and stuff, tend to not be very securely built. So there's actually ways to do CSRF on those. You can read about it all you want there. This one is like a really old slide that I've kept around because I find it pretty funny. Does anyone remember when YouTube had a friend and family list? Because I certainly don't. But apparently back in 2008, there was a CSRF vulnerability on YouTube where you could add people to your family list. Okay, fun. I would imagine this no longer exists, but it does hit major websites too. Okay, that's fun. But yeah, this happens all the time. Here's the one from Facebook in 2009. It's been around forever. But all of them have the same origin, which is, I shouldn't have said same origin. All of them have the same cause, which is that I am tricking the user into making a request that they did not intend to make. Right? Like if you read this article, what does it say? The attack involved the HTML image tag residing on the site. So they were using that image source trick to make people make GET requests. Okay. And even, when you make that GET request, it's even returning an image. So you can't even tell that something has gone wrong. So they were really tricky about it. Okay. So that's CSRF. That's the attack. All of it really boils down to if you trick the user into clicking a link or making a request and the cookies get automatically attached, the server has no idea of telling whether or not the user was tricked or whether or not the user really meant to send $900 to malware. Because how could the server know that? The request has been made, the cookies are attached. So from the server's perspective, it's totally good, totally legal. Okay. Questions about CSRF before I talk about defenses? Okay. I am almost there. So there are 3 defenses that we're going to talk about. And these defenses are all server side. So interestingly, the CSRF defense actually has to happen on the server's behalf. And so here, the server is going to try and add an extra piece of authentication. So what was the main flaw that made CSRF a problem? Well, the problem was that if you sent a request and the request had the right cookie, then the server just had to accept it. If the session token was correct, the server would say, hey, I know you. You're the person who just logged in, and I'm going to accept your request. And so that was not enough. So in these defenses, we're going to try to add extra security, extra information, so that now it's not enough just to send a session token for the server to know who you are. You need to send an extra second secret value for the server to know who you are. And that second extra secret value is called a CSRF token. So now there are 2 secret values. The session token is still there. I'm not getting rid of it. However, this time, I'm going to add a second secret value. So how is this going to work? I'm going to request the secret value as the user. I'm going to request the secret value from the server. The server is going to give me a bonus secret value. So it's not just the session token, but also a bonus secret value that only I know. And my request is going to have to manually attach that bonus secret value in order to be accepted as valid. So the cookie itself, it was too automatic. Attaching that cookie automatically was not good because now the attacker can trick anyone into making a request and automatically attaching the cookies. But the CSRF token is going to be a little bit more difficult. So it's not going to be bundled in a cookie because cookies were automatically attached. We're going to put it somewhere else. It's a little bit more difficult. So maybe like the header, the get parameter, one of the arguments in the get URL, the content, the data, and the post request. So here, this extra secret value is not automatically attached. Someone needs to do a little bit of extra work in order to send this value to the server. And this second value, which is not automatically attached, is what's going to stop a bunch of CSRF attacks. So here's an example that I like, which is, say you want to fill out a form. So if we had no defenses, a form is vulnerable to CSRF. Why is that? Because so first we should say that forms usually are post requests, right? When we submit a form, we click the submit button, the data gets sent over as a post request. So what can the attacker do? The attacker can make you visit their website and have some JavaScript on their website. And what will the JavaScript do? The JavaScript will create a brand new form. JavaScript can do that. the JavaScript will fill in the form with all sorts of malicious fields like to Mallory, $100, and so forth. And JavaScript can fill in the form, and then JavaScript can make you submit that. And all of this is running where? The user's browser, the victim's browser. So the attacker's JavaScript is running in the victim's browser. It's creating a brand new form on the victim's browser. It's filling it in with all the right fields, Mallory, $100, and then it's submitting a post request with the user's cookie attached automatically. So that's how a form might be vulnerable to CSRF. So how does CSRF token stop this? Now I'm going to add an extra value that's not stored in the cookie. So now when I request a form, the form's going to have all the usual fields: name, amount of money you want to send, who you want to send it to. It's going to have all those same fields, except it's going to have an extra field where it's going to say, hey, in that HTML response or HTTP response, I gave you another secret value. It wasn't just the cookie, but I gave you a secret value specific to this form. So when you submit this form, please also attach that secret value for me. And only if you give me the right secret value will I be convinced that you are who you say you are. So now, what's the attacker going to have to do? Well, the attacker is going to have to make a brand new form, just like they did before. They're going to have to fill in all the fields and then make the post request, except how is the attacker going to know what to put in that CSRF token field? They don't. The attacker doesn't know what to put there. So now the attacker is no longer able to fill in all the fields of that form in a way that the server accepts. Server could try to, or the attacker could try to put in their own CSRF token, but it doesn't match, right? Each token is unique to a user. So the difference between the CSRF token and the cookie, the session token, is that the CSRF token is something that's embedded somewhere else. Form field, HTTP header, it is somewhere different so that the attacker has a harder time getting it to be automatically sent. It takes more work to send it. Now, usually this is still automated to some extent, right? Like I've never had to type in a CSRF token, but adding this extra secret field that's not automatically sent the way that a cookie is automatically sent is going to help me stop CSRF attacks. That's the high level idea. Okay. So that's one attack or one defense. Okay. The user logs in, gets a token, and when the attacker says make the request, we make the request. So this is regular CSRF. However, if I add in this extra step where I get the CSRF token in step 2, now when the attacker tells the user, hey, make this request, fill out the form with these fields and send it, the attacker is not going to know what to put in all the fields because there's that extra secret field, the CSRF token field, which we can make hidden so the user doesn't have to see it. And now the attacker doesn't know how to fill in the entire form, so they cannot trick the user into making a legitimate request because that CSRF token is not automatically attached. The burden is on the user or the user's browser or the attacker to manually attach that token. So it's a little bit of extra work. The user almost always never notices. The browser tends to do it, but now the attacker's life is a lot harder. Okay, great. So that's maybe the most common and strongest CSRF token, or sorry, CSRF defense, the CSRF token. So the second defense that we're going to talk about, it works, but it's definitely not as bulletproof or as strong as the CSRF token. So here we're going to take advantage of the fact that the HTTP request that gets sent often contains a lot of information about the request. So we know that the HTTP request, it has what? It has like the get and post parameters. It has the URL path that I'm sending the request to. So there's all these different parameters, including lots that we didn't talk about. And here's one that's pretty useful. So the HTTP request usually involves a lot of information about like the metadata. I guess I'll sit down so I don't like collapse. Okay, it's pretty cool. Maybe I'll just sit down for the rest of the semester. It's pretty chill. Okay, so the referrer header is one of the many metadata fields in the HTTP request. So the HTTP request might say things like, this request was made using a Firefox browser, or this request was made using HTTP version 1.0. But specifically, one little piece of metadata that the HTTP requests tend to attach is, where did this request come from? Like, what web page was I sitting on when this request was made? So for example, if I am on facebook.com and I click a link, then the referrer header will say, this HTTP request was generated by somebody who was sitting on facebook.com on their browser and clicked a link there. So sometimes the HTTP request will automatically bundle this information. It could be for tracking purposes. It could just be to keep track of where the requests are coming from, do analytics. But sometimes people will attach this. Or say, I don't know, I go to the Facebook homepage and I type in my username and password and I send it. The referrer header will say, this person the way that they made this request, or the way that the request was triggered, was that they were on www.facebook.com. They typed in their username and password, and then they sent it off. Click the submit button. And this works for malicious things too. So for example, if you're on, say, like a forum, and someone makes a post with a malicious IMG tag and you make the GET request, then the refer header will say, the reason why this GET request was triggered in the first place was because the user was on that forum, saw the IMG tag, made the GET request. So the refer header, roughly speaking, tells you where the request came from. Or say you're on an attacker's website, and the attacker's website runs some JavaScript that triggers a request. The refer header would say something like, this request was made when the user was on the attacker's website and made a request. So that's the refer header. It gives you some clue as to where the request came from. And if you're wondering why it's spelled wrong, it should have 2 R's, not 1. Apparently someone typoed it and no one has fixed it. So refer header with 1 R. Okay, doesn't really matter though. But it is kind of funny. Okay. So what is this thing good for? Well, the refer header can give the server, and again, the server is the one doing all this defense stuff. It was the one that implemented the tokens. Server is also the one that implements the refer header. So the server can now use the refer header to get a clue as to whether or not this was something the user actually meant to do, or whether or not the user just got tricked. So this might offer the server a little bit of an insight into what the user was thinking. For example, if I receive a request, a login request, say, and it comes from bank.com/login. In other words, the refer header says the user was on bank.com/login, fill out the form, click submit, and the refer is bank.com/login. Then as the bank server, when I see this request and I see that the refer is bank.com/login, I might think to myself, you know what? This user made the request from my website, the bank.com website. So I feel pretty good about this. I think the user was really on my website, made the login request. So I think this is legitimate. I don't think this user was tricked. However, if I receive a login request with a username and a password, and its refer is like evil.com, well, then now the bank's looking at this and being like, wait a minute, why did the user go to evil.com and then try to send a login request to me, the bank? I don't like this. I don't think this refer makes sense. So I'm going to reject this login request. I'm not going to accept it. Or I'm going to reject this money transfer request or whatever. So one possible policy is that when you check the refer header, you allow the request if the refer is from the same website. So if you're bank.com, you only accept the requests that were made as a result of someone sitting on bank.com and making a request. And you do not allow cross-site requests. So you do not allow someone to be on a different website like evil.com and send a request to bank.com as a result of sitting on evil.com. And this is all server side, right? It's the server's job to use the refer and clue themselves in to whether or not the user meant to make the request or if they possibly got tricked. So refer header seems great. Seems like I have a way to distinguish whether or not the user was being tricked or whether or not they really meant to log in or transfer money. But there's a problem. And the biggest problem is that the refer header is optional. There's no requirement that the refer header is correct or filled in. It could be blank. And so one reason why the refer header might be blank is because the refer header might leak private information. So for example, say you're on like Apple's internal website. I don't actually know if this is their internal website, but say this is. And if you were on this website and you submitted, I don't know, a form or something, then the refer header would say, hey, that user was sitting on this top secret Apple URL before they made the request. Suddenly you've leaked information about like Apple's top secrets, probably bad. So sometimes people will strip the refer header and delete it before sending the request on. So some browsers have security settings and privacy settings where you can actually strip away the refer header and leave it blank. So that when I make the HTTP request, instead of honestly filling in the refer like everyone was hoping, I can just leave it blank. The HTTP request is still valid. It doesn't require the refer header to be filled in. Still a valid request. But now the server is now in a bit of a pickle because the server gets a blank refer header. So what does it do? Was this really an intentional request on the user's behalf? Was this the user being tricked? I don't know because the header is blank. It doesn't tell me any information because whoever made the request stripped the header away. So now I have to figure out, do I deny things that have a blank header? Do I accept things that have a blank header? There's a trade-off. If I accept everything, then maybe it's less secure, but more usable. If I deny everything, maybe it's more secure, but it's less usable. So now I have a bit of a struggle to decide when the header is blank, what has to happen. Okay. That's refer header. The final defense is a little bit more modern. I guess we don't have too many slides on it, just one. And so this one's called the same site cookie attribute. This is another attribute inside a cookie. So remember how cookies had they had domains, they have paths, they had secure, they had HTTP only. They have one more. It's called same site. And it functions kind of similarly to the refer header. But the refer header was for HTTP requests. Same site is for cookies. And so the same site says, when I dig through the cookie jar to decide what gets sent or what doesn't get sent, don't just check for the domains and the paths being valid. Make an additional check and make sure that if I'm sending a cookie to evil.com, when I'm sending a cookie to evil.com, the domain of the cookie needs to also match evil.com. Or when I'm sending a cookie to, I don't know, bank.com, the domain of the cookie needs to exactly match bank.com. So this is a stricter check between the cookie domain and the domain of the origin you're on. So sorry, I may have messed that up a little bit. So one more time. Same site doesn't check, it not only checks who you're sending it to, so that's what all cookies check. All cookies check if you're sending to bank.com or google.com or mail.google.com as we saw. But the same site flag additionally checks what website you're currently on as you make the request. So if I'm sitting on evil.com and I make a request to bank.com, the same site cookie attribute will say, well, in general, I would send the bank.com cookie because I'm making a request to bank.com. But because you've specifically told me that you should only send cookies conservatively and only send if I was sitting on bank.com and made a request to bank.com, I'm actually not going to send the cookie. And the reason why I'm not going to send it is because I was sitting on evil.com when the request to bank.com was made. If same site is set to strict, the only way in which the cookie will be sent is if I was sitting on bank.com and I made a request to bank.com, then the cookie would be attached. So that's the same site cookie attribute. I believe most modern browsers have it. Probably just like Microsoft Edge or Internet Explorer at this point doesn't have it, but it's kind of like coming down the pipeline. It's another way to defend against CSRF attacks. Okay, awesome. I'm almost done. So quick summary on cookies, and then I'm going to go take a long nap. So cookies were a piece of data. It's just a name value pair with a lot of different attributes. And the reason why cookies exist is because we want to be able to maintain state across multiple requests. If I would like the website to be dark mode and I order the website, please be dark mode for the rest of time, the server is going to send me a cookie. I'm going to store the cookie in the browser's cookie jar. And on all future requests, this browser will automatically attach the cookie. And that way the server can customize its response and make the background look dark or whatever it is I requested. So it allows independent HTTP requests to stop being independent. We talked about these rules, and the important thing is really not the specific rules, to be honest, but the important thing here is why these rules exist. So anyone can just tell you these rules and you can just write them down on your cheat sheet and memorize them. The important thing about these rules is that they're trying to stop attacks where cookies are allowed to affect unrelated domains. So I don't want evil.com to be able to set a cookie that affects google.com. I don't want evil.com to be able to change my dark mode settings everywhere or like log me in on all sorts of different places. That would be bad. And similarly, I only want to attach relevant cookies. I don't want to send my google.com session token top secret to evil.com. So the cookie policy restricts what cookies do I accept. I don't want to accept evil.com sending me unrelated crap. And I don't want to send unrelated stuff. If I'm making a request to google.com, I'd better only send the cookies that are relevant to my current request. Talked about session authentication, a particular implementation, or like a particular idea that's implemented by cookies. So session authentication could be implemented all sorts of different ways, but cookies are the most natural way. And again, cookies are not the only thing you can, or session authentication is not the only thing you can do with cookies. You can do all sorts of different things, but session authentication is one of them. We can think of it as the first time you log in, you send a username and password, receive a session token as a cookie, and then in the future, you automatically attach that cookie. However, we have to be careful because that session token is you. It's you being logged in. If someone steals it, they can now log in as you. So you have to be really careful about keeping them secure and not sending them to the wrong place. We talked about CSRF. It's a fancy attack, got a fancy name, but all that it is you're tricking the victim into making a request. The request automatically attaches cookies, and the server has no idea whether or not you really meant to send it or whether or not you got tricked into sending it. And this could be a GET request, could be a POST request, as long as the attacker tricks you into making the request. And we talked about the 3 defenses. Token is an extra secret value that the attacker does not know, but needs to fill in themselves, so it's no longer automatically attached. has to be filled in by the user or the attacker. Now the attacker doesn't know the secret value, cannot fill it in when they're tricking you into making a request. Talked about the refer header and the same side cookie, which gives you a rough clue as to where the request came from. Okay, that's it. Thanks for sticking with me as I like sniffled the whole time. So I'll see you on Monday, maybe. Okay.